Electrostatic force and its main features have been known for quite some time. Eventually, like most other ideas, there came a time to describe it mathematically. So Charles Coulomb came along and did just that. Say we have two charges, Q1 and Q2, that are separated by some distance r. We know that there is either an attractive force or a repulsive force based on whether or not the charges are the same. What we are interested in is the magnitude of that force. The magnitude of this force depends on some universal constant times the amount of charge each point holds divided by the distance between the 2 points squared. The constant works out to be 8.988 times 10 to the 9th newtons meters squared per coulomb squared. So we can use this to determine the force of attraction between an electron and a proton. The average distance between an electron and proton in a hydrogen atom is 0.530 times 10 to the negative 10th. We can take our equation and figure out what we already know. The constant is a given. The charge on an electron is 1.60 times 10 to the negative 19th coulombs, as is the charge on a proton. Since we are ending in an absolute value anyway, we don't really need to worry about the sign of the charge. We also know the average distance between the two as 0.530 times 10 to the negative 10th meters. Plugging all that in, and we get 8.19 times 10 to the negative 8th newtons. While at first glance this doesn't appear to be, this is actually a very large force for an electron. We could get a better perspective if we use it to determine the acceleration of the electron. The acceleration ends up as 8.99 times 10 to the 22nd meters per second squared, which is pretty darn fast. Now, Coulomb's law is describing the attraction between two charged particles. It wasn't very long before this relationship started being compared to the gravitational attraction between two objects. In fact, when you look at the two equations, they are extremely similar. We can find the force of gravitational attraction between a proton and an electron simply by plugging in the different values. This gives us a gravitational force of 3.61 times 10 to the negative 47th newtons. Looking at that exponent, you can even say that the force of gravity is negligible on particles such as electrons and protons. Compare that to the force between the particles, and it's easy to see that which has the greater effect. And actually, if we put that into a ratio, we find that the electric force is 2.27 times 10 to the 39th power larger than the gravitational force. So on a small scale such as this, gravity is negligible, and the individual charges are much more important. If you compare the large scale, say between you and the Earth, gravity, of course, is much more important. Think about that for a second. Do you have a charge? Does the Earth? Since we are pretty much electrically neutral, the attractive and repulsive Coulomb forces are going to cancel each other out on those larger scales. Say you and a friend are 8 meters apart. You each have a balloon that has a negative 2.5 millicoulomb charge associated with it. What is the electrical force between the two balloons? Well, we know that the distance between the two balloons is 8 meters, and we know that the charge on each balloon is negative 2.5 millicoulombs. Since we always know that K is 8.988 times 10 to the 9th, all we have to do is plug in our unknowns. We find that the force between the two balloons is 878 newtons. Now say you and a friend are 4 meters apart. His balloon has a charge of negative 33.7 coulombs and repels your balloon with a force of 626 newtons. Now say you and a friend are 4 meters apart. His balloon has a charge of negative 33.7 microcoulombs and repels your balloon with a force of 626 newtons. What is the charge on your balloon? In this case, we only know one of the charges, but we also know the force it is applying to the other balloon that is 4 meters away. A little algebra, and we rearrange Coulomb's equation to solve for the second balloon's charge. From here, we know everything else and can plug in those values to find the charge to be a negative 0.00331 coulombs. So Coulomb's law is simply the mathematical description of an electrostatic force between two charged particles. It relates the magnitude of the two charges to the distance between the two charges to a known constant to determine the force acting on each individual particle.